So let's look at more in detail about a biasing network for amplifier. Essentially, the biasing network is used to set the quiescent point, namely the Q point, the so-called quiescent point, which determines when there is no RF input, what will be the current that is flowing, the corrector current that is flowing through the amplifier. Through the transistor. So this bias network can be set either using a passive network, using passive circuit elements like using resistors, inductors and capacitors, or can be realized using an active device using transistors. So we are going to be looking at the first kind, which is realized using resistors. Essentially, a resistive divider network is used to set the bias condition for the Q point for the transistor. Coupled with that are what are called as inductors and capacitors. The inductors have a specific name here called as, the inductors are called as RF chokes. They are called as RF chokes. That means they don't allow RF to pass through. The reason being, the reactance of an inductor is omega L. Notice that we don't write the J here. It is XL is going to be, the reactance of an inductor is going to be omega times L. And this value is going to be pretty high when omega is high. So in that sense, this blocks, the inductor blocks high frequency RF. It blocks RF. The inductor blocks RF. How about a capacitor? A capacitor, the reactance of a capacitor is minus 1 over omega C. And as omega increases, this reactance decreases. So in essence, a capacitor blocks DC. When omega is 0, then XC is, when omega equal to 0, then XC is equal to infinity. So means a capacitor, in other words, a capacitor blocks DC, but the value of omega, when it is so high, then XC becomes very close to 0. Then it means that it becomes a short circuit for the RF. So it can bypass the RF, blocks DC, and it is bypass, or it's a short circuit, or in other words a short circuit for RF. So based on that, we can analyze any transistor circuit that you see here. For example, what's given here with a certain bias condition of VCC R1 R2. The choke, essentially, if we were to analyze this circuit for the DC performance, just the DC case, in the case of DC, that means for the RF, this inductor is going to be an open circuit and the capacitor is going to be a short circuit. If we were to redraw this and analyze it in the case of DC, then we can clearly see that this transistor is essentially this RFC at the base is going to be a just for the case of DC, it's going to be a short circuit because omega equal to 0. This case is omega equal to 0. So in DC, this is going to be a short circuit, while for RF, it would have been an open circuit. Then the capacitor would have been an open circuit for DC. Yeah, a capacitor would have been an open circuit. So essentially, there is no current here. It's going to be an open circuit, whereas there is this resistance R2 over here. The resistance R2 over here. And this RF choke would have been a short circuit for DC as well. And then we have this resistance R1 here, and this is going to be the VCC. In essence, this capacitor is going to be an open circuit, and this capacitor here is going to be an open circuit for DC. This is how this circuit is going to look at for DC applications. Notice that this RF choke is not going to allow any current, RF current, to pass through above. So all the DC current can still flow through, but the RF current will not pass through here. Instead, it is going to be delivered to the load. Similarly, whatever the RF input that you're going to give in is going to flow through the transistor, but the RF choke is not going to allow it to pass through. It's not going to allow it to pass through here, but all the RF current is going to flow through the base. So we can analyze, we can take an example like in this situation, we want to design a passive bias network, meaning we want to design the R1 and the R2 such that under the bias conditions, the collector current is a DC of 10 milliamperes So this one is a DC current. The collector emitter voltage is 3 volts across the collector and the emitter. This is 3 volts. VCC is 5 volts. This is 5 volts. Assume that the transistor has a current gain of 100 and the VBE is 0.8 volts, the drop between the base and the emitter. We know that the base current is going to be the collector current over beta. The I1, the transistor that is flowing from the supply, the current that is flowing from the supply is going to be IB plus IC, applying the Kirchhoff's current law. Whatever current that flows in here is going to split into the base current, which is essentially going this way, because if you look at the DC equivalent circuit, the I1 that flows here splits into IB, the base current, and the collector current, and that in terms of beta is going to be 1 plus 1 over beta, and when we work it out with the values of beta, it becomes 0.1 milliampere. So if I1 is 0.1 milliampere, we can go ahead and, given the value of VCC is 5 volts and VCE is 3 volts, we can find the value of R1, because this VCE is 3 volts and this VCC is 5 volts for the DC. We can figure out what should be the value of R1, so that the potential difference here is 5 minus 3. So it's going to be VCC 5 minus VCE 3 over I1, which is the current that is flowing here that we just figured out from the previous step, and that would have been 198 ohms. Similarly, we can figure out R2 to be this base voltage VBE is known, this voltage here is known, so we can find as VCE minus VBE. The potential difference between across the resistor R2 is going to be VCE minus VBE over IB, the base current that is flowing through that resistor, and that would be 22 kilo ohms. That the essentially finding R1 and R2 is what is about designing the bias network.